Okay, so today we're going to deal with the last topic on chapter 4 in the textbook, which is the mass spring system. So, as I mentioned last time, the homework attached to this lesson is actually not that long, but there is lots to talk about, in order to understand the physical setting that leads to this application of the second order differential equation. So the mass spring system is an important model in physics because this type of motion or the setting appears in various contexts. Although we're going to use as a model, as the title says, an object connected to a spring, the so-called mass spring system, the type of motion described by this setting actually appears in various situations when you don't actually have a physical spring, but the object behaves more or less in the way this system behaves. So in the first part of the lecture, we're going to deal with how to describe the motion of the mass spring system with differential equations. And then obviously we're going to go over some examples and classifications on the type of motion you have, also connected to the types of solutions. And it's important to remember at the end of this lecture you're going to have a Camtasia demonstration with some examples that we run on Maple. So it's very important in this lecture to actually run all the examples that I go over in this video lecture. Run it with Maple. There is a Maple template in Blackboard that I actually made available. Just download it and run it yourself. So on Camtasia I'm going to show you how to run those examples with Maple. It's very easy, just a matter of replacing some constants with your new numbers and then running Maple applet, Maple template, and then graphing the solution. So let's get to the root of the description here of the experiment. So you have an object of mass m which is attached to a wall via a spring. So eventually basically you want to describe the motion of the object if you depressed or stretch the spring a little bit and then let the object move. So the only forces that are involved in the motion of the object are the forces in the spring tension, and the damping. So there might be some friction or damping between the object and the floor. So the physical constants that are involved here again are the mass of the object, m, which is obviously greater than 0. That's important. All of the constants will be positive in this case. You're going to have the spring constant. The spring constant basically describes the tension in the spring. It's connected to the so-called Hooke's law, right? Which, depending on the displacement of the object, then you have a certain tension in the spring that acts on the object. And then, of course, as I mentioned, the damping constant, denoted by B, the damping force, again coming from physics, this is going to be proportional to the velocity, and that's the damping constant, which describes that force. So one important remark I want to make here, when we formalize the differential equation that describes the motion here, again, as with all differential equations, it's important to describe what we mean by the dependent variable, by y of t. So y of t is the displacement of the object, but because the displacement is caused either by compressing the spring or stretching it, we're going to make the convention that if the displacement is positive, then the spring is stretched. In other words, displacement positive means that the object is displaced to the right hand side. Right? So that means in this way I wrote it here, the spring will be stretched. And y of t less than 0 means that the spring is compressed. Right? So the displacement negative means that I move the object to the left side, and by that I compress the spring. So that means when the displacement is 0, means the object is in equilibrium. So there is no motion, right? I mean, the spring is neither stretched nor compressed. So basically here, if you imagine the spring is in the relaxed, disturbed position, this will be basically the origin of the system, right? So the origin of the coordinate system. So how do I describe the motion of the object? So again, the experiment is you either stretch it or compress it, and then you let it loose, or maybe you give it an initial velocity, but then you let the object move according to its own devices, right? I mean, according to the forces that act on the object, which in this case are the damping force and the spring force. So we know from the Newton's law of motion that the mass times the acceleration is equal to the total force, basically the resultant force that acts on the object. In this case, again, damping and spring tension. One important thing to keep in mind is that these forces will always act in the opposite direction of motion. Okay, so think about this. If I move the object to the right, the damping and the spring constant try to push the object backward to the left. If I compress it, damping and the spring constant will act in the opposite direction. So that means when I write the equation of the mass times acceleration equals total force, this will be of opposite signs always. So mass times acceleration is m times y double prime. So remember, the second derivative is the acceleration if y represents displacement. And then this has to be equal to the damping, which is again proportional to the velocity, but again with the opposite sign because it's in the opposite direction. So by prime will be the damping force, and the spring force, according to the Hooke's law, again it's k times y, right? So that's spring constant times the displacement. So that's going to be the spring force or tension in the spring. So I want to point it out, that's how the equation is set up. Obviously, when you solve it, you move everything on the left side because you immediately recognize that this is nothing but a second order linear homogeneous ODE. But it comes from this setting, right? Mass times acceleration equals total force responsible for that motion. So then if we move everything to the left side, we basically arrive to what is already familiar to us, a second order differential equation with constant coefficients, homogeneous, right? So I mean, if nothing else acts on the object, which we're going to change later, but for now nothing else acts on the object, then there's zero on the right hand side. So we know already how to solve this via the characteristic equation and all that kind of good stuff you learned already from the previous lessons. The question is how to describe this motion from a physical perspective. So notice I use slightly different notations here for these coefficients because they have this physical meaning, right? So I mean, m always means the mass, b means the damping, k means the spring constant. So you can always put this into the equation once you have this information given in the problem, right? So I mean, if the problem says the mass is 1, spring constant is 4, let's say the damping is 5. It's important to make sure you place these coefficients in the right position. Doesn't matter in which order they are given in the problem, right? Mass goes with y prime, so that means 1 times y prime. Spring constant is going to be the last one, right? Because it's with y, and the damping is with y prime, right? So 5y prime plus 4y equals 0. And then you can proceed and solve this and find the equation of motion. In fact, this is actually easy to solve. Let's just do it. So r squared plus 5r plus 4 equals 0. This factors nicely into r plus 1, r plus 4. And then, of course, the roots are minus 1 and minus 4. So the equation of motion, or the displacement of the mass attached to the spring, will be in the form of c1 e to the minus t plus c2 e to the minus 4t. So what is C1 and C2? Well, that has to come from initial conditions. In this case, the initial conditions will have a very specific meaning, right? So y of 0 will be the initial displacement, and then y prime of 0 obviously will mean initial velocity. So for example, if I said I just displace this object and then I let it loose, that means the initial velocity is 0, so then the initial displacement, of course, will have to be specified. So let's not worry about with this. We have plenty of examples before this on how to solve this. I just want to focus on some important properties before moving on with some other topics on this concept. But anyway, the meaning of this will mean the displacement at time t. I want to point something very important before we move on. Notice these roots are negative. So if t goes to 0, if t goes to infinity, in other words, if you let the object move for a long time, doesn't matter what c1 and c2 are, so it doesn't matter what are the initial velocity and displacement, eventually y of t approaches 0. Right? Because if I let t goes to infinity, these negative exponentials means that I have minus infinity at the exponent, and remember from calculus 1, e to the minus infinity means limit that is equal to 0. This should not be a surprise to any of you, again, who focus on the meaning of the physical meaning of the experiment. So I disturb that object, I let it loose, and then there's some damping in the system, and then this solution says eventually the displacement is 0. So eventually, after some moving around, the object approaches the equilibrium. So that's not a surprise, because the damping will always bring the object to a stop. Again, if it's the only force that acts on the object together with the spring constant. These are forces that dissipate essentially the motion eventually, right? I mean, they always act against the direction of motion. So again, assuming there's nothing else acting on the object, because we can certainly change that later, the object always comes to a rest. So the math, if it's set up correctly, should always reflect this property that the object comes to a rest. So I want to point out why actually this is obvious from the math perspective, right? I mean, the physics clearly states that that's what should happen, right? But how can we tell mathematically that indeed the system always comes to a rest? Well, remember when you solve for the characteristic equation, right? When you set up your quadratic equation that gives you r, the fact that m, b, and k are always positive is what caused the root r to be negative, or if they're complex, they will have a negative real part. So it's an immediate consequence of the fact that these are positive, and they have to be because they're physical constants, right? I mean, you cannot have a negative mass or a negative damping coefficient. So they're always positive in the case of a mass spring system. And so if they're always positive, if you look at the formula for r, again from the quadratic formula, it's not that hard to see that these are always negative if they're real, or they have negative real parts. So if these are real roots, so if this quantity is positive, okay, so pause for a moment, if this radical is positive, the radical is less than b, because you subtract something from b squared. Okay, so something less than b that you add to minus b, then is going to be a negative number. So if it's minus between these guys, it's negative, obviously. But if you have plus, the overall numerator is still negative because the quantity under the radical is less than b. So R1 and R2 are negative if real, and if complex, alpha, the real part, is minus b over 2m, which is also negative. So remember, alpha appears in the solution in the complex case. We're going to have a classification immediately, but the exponential has e to the alpha t in the complex case, and again that exponential is negative, and it will cause the solution to approach 0. So in fact, let's just write formally how the solution looks like in the complex case. It will be e to the alpha t c1 cosine of beta t plus c2 sine of beta t. So that's the complex case. And if alpha is less than 0, again y goes to 0. Now the difference between the real and the complex case might be this it's going to be this oscillation part due to the cosine and sine of beta t. So basically, but overall this goes to 0 because of the exponential. But unlike the real case, when you have this example here, the solution may go to 0 without oscillations. So in the next part of the lecture, we're going to make this classification of the type of motions you will see in the mass spring system. But let's just anticipate a little bit with two simple graphs. So essentially, in the real case, the solution may approach zero without any oscillations. There might be actually one step over the equilibrium position, so like going over the equilibrium position once, but not more than once. So the solution, no matter where it starts, approaches zero without oscillation. So this will be the real case when you have real roots. In the complex case, when you have complex roots, the solution goes to zero, but it does so via oscillations because of the presence of those sine and cosine beta t. Again, make sure you run the examples with maple because they will look obviously better than what we can do on the board. So this will be the complex case. So you may wonder, why do we care about this and why do we have this careful classification about the motion and whether we have oscillations or not? Well, there are lots of examples in practice when you actually care about that. You may want oscillations or you may want to avoid them. So for instance, skyscrapers are designed to oscillate under the wind in order to eliminate internal tensions. So a certain type of oscillations is actually necessary. So if your system acts like a mass spring system, you want to be in the situation when you have oscillations. On the other hand, for example, in the front suspension cars, you have something called struts, in the springs, and the role of those are like pistons. The role of those devices are that when you step on the brake suddenly, you don't want the car to bounce around back and forth because that's not safe, basically, right? So you want to prevent oscillations. So then you want to have enough damping to prevent oscillations, but then the question is, how much damping should you need? Because more than you need, again, that's not good. That may cause unnecessary internal wear and tear. Lots of other examples. Wings of airplanes are designed to oscillate under stress, again, to not cause internal tension in the material and break. Even the propellers, the blades of the jet engines are actually designed to oscillate under impact, because that's what makes them actually absorb possible objects like birds, and not lose too much power so that the plane can still fly. So that is the reason why we do have this classification of the type of motion. And on the next part, we're going to do just that. We're going to basically write down the various types of solutions and how they look like, generally speaking, and whether we have oscillations or not, because we have specific names for mass spring systems under those configurations, depending on whether you have oscillations or you don't. So stay tuned for the second part.